internet, but welcome to tonight's Deep Space Dialogues. Our talk tonight, discovering the least massive brown dwarfs known with the James Webb Space Telescope, and our speaker is Dr. Kevin Luhman. I'm your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. And as always, we want to thank the team behind the scenes, which unfortunately Chad Smith is gotten sick today. He's down with a really bad cold. So Ralph Crawford is running this solo. Everyone give a big hand for Ralph because, he's he wasn't really trained to do it solo, but he's going to do it solo tonight. So thank you very much, Ralph. Our next Deep Space Dialogues event will be on March 18th, 2026. And we are going to have somebody who was formerly at Space Telescope and is now out at JPL, Klaus Pontoppidan. And he will tell us about what Webb is showing about planet formation. And keep that in mind because we're going to talk about brown dwarfs here. We're going to talk about planets next month. So the two are kind of related. You'll get that through. All right. If you want to be notified of all this stuff, and keep up with our Deep Space Dialogues as well as the other videos that we are posting. Follow our YouTube, subscribe to our YouTube channel, Space Telescope Vision. And this is our YouTube channel, and the Space Telescope Science Institute. And we have hundreds of videos available there. But most importantly, we have all of our previous Deep Space Dialogues available for you to watch in a playlist. This is the 6th of our Deep Space Dialogue. So, hey, we are getting lots of stuff through. Now, there's one more thing you need to remember tonight, and that is that we want your questions. Okay, this is supposed to be a dialogue. Yes, I'm the one hitting here who's going to ask your questions for you, but I have a lot of my own questions, but I want your questions to ask our speakers. So please add them to the YouTube chat during the talk and we will ask our speaker. All right. So Kevin, welcome. Happy to have you here tonight.
I'm happy to be here.
All right. So you are going to talk to us about your research, right? Tell us a little bit about yourself first. You're at Penn State now, and where did you do your schooling?
So I grew up in Kansas, and then I was an undergraduate student at the University of Texas in Austin, and then a graduate student at the University of Arizona in Tucson.
Okay. So did you grow up thinking that you were going to be an astronomer when you were in Kansas? Let's see, who's the famous astronomer that grew up in Kansas? Oh, no, it was Illinois. That was
Clyde Tombaugh is from Kansas.
Tombaugh. Is he from Kansas? Okay, I couldn't remember whether he was from Kansas or Illinois. So yeah, so Clyde Tombaugh was like a Kansas farm boy that became an astronomer. Mm-hmm. Was he your hero?
I'm not sure if I knew about him when I was young, but like a lot of astronomers, I developed an interest in astronomy when I was very young, and for me. A big influence was Carl Sagan and his Cosmos series, because that came out when I was a young child.
Cool, fantastic. I remember watching the original Carl Sagan Cosmos series back in the late 70s, early 80s?
Right.
Yeah, that was a lot of fun. Uh-huh. That was cool. All right, so tell us something special about yourself. What do you do when you're not studying the universe?
So since I'm from Kansas, I'm a big Kansas Jayhawks fan, so I closely follow their basketball team.
Okay, I had a friend who really hated Kansas, and he always called them the Chicken Hawks.
That's from Oklahoma.
All right. Do you do any special sports for yourself, or any special hobbies that take you away from your scientific endeavors?
Well, Central Pennsylvania is a pretty nice place for hiking, so from time to time I go hiking in this area.
Right. Pennsylvania has a lot of great state parks.
That's right.
Yeah. Okay. Well, let's put up your slides, and then we can go to talk about what you're going to talk about today. So, discovery of the least massive brown dwarfs known with J2ST. And that, of course, begs the question, what is a brown dwarf? And actually, I've looked at your slides already, so I know that your first slides cover this. So why don't you go into it with your slides and get at least that question answered?
Sure. So as implied by this first slide, stars exist over a wide range of masses. There are some that are much more massive than the sun and some that are much less massive. A star that has a higher mass has more stuff sitting on top of its center, which means a higher pressure and therefore a higher temperature. So more massive stars are hotter, less massive stars are cooler. Meanwhile, in order to fuse hydrogen in the center of a star, there's a minimum temperature of about 10 million Kelvin that needs to be achieved. So that means that, in theory, there might be stars that are too small in mass and too cool to achieve that minimum temperature for fusion.
Okay, so you're basically stating that, all right, the larger stars are the hotter ones, right? But the smaller stars might not be able to get up to this 10 million Kelvin.
Right.
Okay.
And stars that are born too small in mass and too cool to fuse hydrogen, those are called brown dwarfs. So a brown dwarf is a star too small in mass to fuse hydrogen.
Now, I've heard them called failed stars. Is that proper, or is that not kosher to do that?
Yeah, some people use that terminology. I feel like it's a little bit too negative. And it turns out that the boundary in mass between stars that fuse hydrogen and brown dwarfs that don't is about 8% the mass of the sun, which corresponds to 80 times the mass of Jupiter. And that comes from the fact that the sun is 1,000 times the mass of Jupiter. And so brown dwarfs, they're very small in mass, very cool, very faint. And so in a lot of ways, they're very similar to gas giant planets like Jupiter or Saturn. In other words, like Jupiter is a big ball of gas like the sun, but it's not hot enough in its center to fuse hydrogen. And so in a way, brown dwarfs and planets have similar characteristics. And because of that, you might wonder, how do we distinguish between brown dwarfs and planets?
Right. I mean, because, neither one of them is fusing hydrogen. Yeah, go ahead.
And so the best way to distinguish between the two is based on how they form. Where a star is born from the collapse of a huge cloud of gas and dust in space, and as it collapses, most of the matter goes into the central object, the star, and then a small amount of the matter stays behind in a disk of gas and dust around the star that forms planets. And a brown dwarf forms in the same way from a huge cloud of gas and dust, but simply from a smaller cloud of gas and dust. Whereas a planet, again, forms within a disk of gas and dust surrounding either a newborn star or a newborn brown dwarf. And so that's how we can distinguish between brown dwarfs and planets based on how they form.
So if you had a really big star, okay, and you formed a planet in the disk, could that planet get large enough to become a brown dwarf?
Well, that's a good question. I mean, you could also ask, could an object form within a disk around a massive star and not only be a brown dwarf, maybe it could even be a low mass star? And so we don't know for sure. The difficulty with the most massive stars is that, first of all, they generate vast amounts of very harsh UV radiation. And so we think that probably destroys very quickly any disk of gas and dust around it. And in addition, the most massive stars, they only live for a few million years before exploding in the supernova. So if any little bodies formed around a massive star, they would very quickly probably be destroyed by the supernova explosion.
Okay. But we also have binary stars too, right? So obviously 2 stars can form around each other. Could a star and a brown dwarf form around each other too?
Yep. So, and so we see many examples of that, of stars and brown dwarfs in binary star systems around each other. That's right.
Okay. And so then I got to go to the great question is, could a planet form around a brown dwarf if we're going through all our possibilities here?
Yep, that's a great question. So the answer is that it's very likely that it does happen. The difficulty is that the various methods that astronomers use to search for brown dwarfs around stars, it's more difficult to apply them to brown dwarfs because brown dwarfs are a lot fainter. And so we only know of a few objects that we think are planets orbiting brown dwarfs, but that's mainly just because it's more difficult to search for planets around brown dwarfs. But we do know of many brown dwarfs that show these disks of gas and dust surrounding them when they're newborn. And so that's sort of circumstantial evidence suggesting that planets probably do exist around brown dwarfs.
Fantastic. Fantastic. All right, we already have a question, and it's a really basic question. Are brown dwarfs actually brown? Why do we call them brown dwarfs? Are you going to get into that later in your talk?
So that's a good question. So the color that any object, a star or a brown dwarf or a planet, the color that it has depends on the wavelengths at which you're looking. So if you look at one range of wavelengths, like in the optical, you might perceive a certain color, maybe red, for instance. But if you look at another range of wavelengths in the infrared, it might look blue. So the color you perceive would depend a lot on exactly which wavelengths you're looking at. But as far as the name brown dwarf, that basically comes from the fact that brown dwarfs don't use hydrogen. So because of that, they're very cool and very dim, and they get fainter and cooler over billions of years over time. Right. And so the brown is supposed to connotate the idea that they're very cool.
Okay. So they don't fully light up. Okay. All right. Sounds good. Why don't you continue on with your slides?
Okay. So one of the most fundamental questions that I want to try to answer about brown dwarfs is, what is the smallest mass at which they exist? Again, the dividing line in mass between stars and brown dwarfs is 8% the mass of the sun, which is 80 times the mass of Jupiter. And so the question is, how small do they go?
Yeah, I mean, how much larger will Jupiter have to be to become a brown dwarf? Okay, go ahead.
Uh-huh. And so, as I already mentioned, stars are born from the collapse of huge clouds of gas and dust in space. And as this collapse occurs, gravitational energy is transformed into heat. And so because of that, a newborn star is very luminous. It's very bright. And that also applies to a brown dwarf. So a brown dwarf, because it forms in the same way, when it's born, it's quite luminous. And that's illustrated on this diagram. So this is showing what's called luminosity on the vertical axis. So luminosity refers to the total amount of energy, the total amount of light of a star or a brown dwarf. And it's plotted in units of the sun, where 1 refers to the luminosity of the sun. So you can think of the sun as being the top of the diagram. And then on the horizontal axis is temperature, the surface temperature of the object. And so here the dot represents...
Okay, so let's just go through this a little bit more, because not everyone's comfortable with scientific notation here. So that 10 to the minus 2 is 1%, 1/100th, right?
That's right.
10 to the minus 4 would be 1/100th that, or 1/10,000th. Okay, and then we're getting like 1/1,000,000th and 1/10,000,000th and such. Okay, so your luminosity scale goes over huge range of luminosity. Right? It's not just like from 1 to 100. It's from 1 to 10 million or 100 billion almost. Really, right?
Right. That's right.
Okay. And then your surface temperature is measured in kelvins, right? Which is the absolute temperature scale. And if you're in science, you know what that is, right? And that's also logarithmic. And that's going lower, right?
It's lower to the right, higher to the left. So okay. The left end of the diagram is 4,000 Kelvin, whereas the sun is 6,000 Kelvin. So the sun would be somewhat to the left of the left edge of this diagram.
Okay. So everything you're plotting on this diagram is is less bright than the sun and is cooler than the sun.
Yep, that's right.
Go ahead.
And so the dot shown here is the predicted luminosity and temperature for a low mass star. So a star that is right at the dividing line between stars and brown dwarfs. And again, as I mentioned, when a star is born, it's quite luminous, but over time it shrinks because of gravity, it collapses, and because it's shrinking in surface area, it gets fainter. But eventually, the center of the star becomes hot enough that it starts to fuse hydrogen, and that halts the collapse of the star, and then the star maintains a stable luminosity. So it just sits here at a stable temperature and luminosity for billions or trillions of years.
Okay, so this process of fusion turning on is a slow. How long does that take?
In this case, for this star, it would take of order like 100 million years.
Okay, so over 100 million years, it collapses, gets smaller, and gets less luminous. But then when fusion fully kicks in, the engine really gets going, it becomes stable.
That's correct.
Great.
And so that's for a star. A brown dwarf at the mass of Jupiter, so that would again be 1,000 times the mass, less massive than the sun. Its predicted luminosity and temperature shown here. And again, because it doesn't fuse hydrogen, it never stabilizes its luminosity. It just cools and fades forever over billions of years.
So it does that same collapse and heats up, but it never reaches the temperature where the engine can really rev. It's like you're just turning that key for 10 billion years. Just never starts.
That's right. So at billions of years of age, brown dwarfs are very, very faint, and they need to be quite close to us for us to see them. But the thing to take away from this is that brown dwarfs are brightest when they're born. And so if we want to try to find brown dwarfs at the smallest masses of which they exist, our best option is to try to search for them in nearby nebula of gas and dust that contain newborn stars.
Okay, so if you're going to see a brown dwarf, the easiest time to see it is when it's a newborn.
That's right, because it's relatively luminous. I mean, when a brown dwarf is born, it basically doesn't know that it's not a star yet. It thinks it's a star. It's only hundreds of millions of years later that it realizes that it's never going to fuse hydrogen. And this is showing an example of a nebula of gas and dust containing thousands of newborn stars.
So that was R136, wasn't that?
I think that might be correct.
Yeah, I'm not a stellar astronomer, but I think I recognize that one in the Tarantula Nebula.
I should know since I have it in my slide. I think that's right.
Okay, we got a question here that says that shows a little bit more knowledge and thing. What about brown dwarfs burning deuterium? Okay, if they get to that deuterium burning level, as asked here, does that produce a pause in the drop?
That's exactly correct. So, first of all, deuterium, that's an isotope of hydrogen that contains one proton and one neutron, and it's much more rare than hydrogen itself, but it can experience fusion. So, if a brown dwarf is more massive than about 13 Jupiter masses, it does become hot enough to fuse deuterium. But that phase of fusing deuterium, it only lasts for a few million years. And so the question is correct. So during that time, during those few million years, the luminosity is sort of stabilized, but that's only a blink of an eye in the life of a star or brown dwarf, a few million years. So very quickly, all the deuterium is consumed, and the brown dwarf just resumes its slow fade over time.
Okay. Yeah, because you were showing it over billions of years. And so if there's a little flat section that's a few million years long, it's not going to change the plot all that much.
That's right.
All right. Continue.
And so now the question is, well, at what wavelength range are brown dwarfs brightest? In other words, what kind of telescope do we need to use to search for brown dwarfs? And so this is showing wavelength on the horizontal axis, the electromagnetic spectrum extending from X-rays to the radio. And on the vertical axis is the intensity. And this is showing a black body. This is a source of thermal radiation at a temperature of 6,000 Kelvin. So that's the surface temperature of the sun. Okay. So the sun is brightest at visible or optical wavelengths.
Right.
A star that would be hotter than the sun would be brightest at UV wavelengths. But brown dwarfs, on the other hand, they have temperatures of hundreds of Kelvin, so they're a lot cooler than the sun. And so given their temperatures, they're brightest at infrared wavelengths. And so that means that infrared telescopes are our best option for searching for brown dwarfs.
Okay. So I know the viewers are thinking, well, do we actually have stars at 60,000 Kelvin?
So there are stars at 60,000 Kelvin. The best examples are the central stars of what are called planetary nebula, and then also white dwarfs.
Okay. So stars really can get that bright, and they can get this cool, but if they get that cool, they're brown dwarfs.
That's right.
And so we're looking in the infrared because, I mean, as you've drawn it here, 1 micron where the 600 Kelvin curve kicks out, that is, definitely that's infrared.
That's right. Well, that's sort of the boundary between optical and infrared. That's right.
Okay.
And so previous infrared telescopes have detected brown dwarfs down to about 5 times the mass of Jupiter. So again, that's like 0.005 of the mass of the sun. But we haven't known whether or not brown dwarfs exist at even smaller masses because we needed a more sensitive infrared telescope. And as you can guess, that's where the Webb telescope comes in. So it's the most powerful infrared telescope launched to date. And so it offers the possibility of detecting brown dwarfs down to the mass of Jupiter or even lower in mass.
Okay. And I assume that's partially due to its size. I mean, you're showing here just how big the Webb mirror is. This is the model that they built down, and this is at Goddard Space Flight Center, if I remember.
Right. So this is not the telescope itself, but it's a life-size model of the telescope. That's right. And so, so it's the most sensitive infrared telescope because it has a large mirror that is in space. And so being in space is key for its sensitivity.
Right. Both its sensitivity and its resolution being, 6.5 meters across, right?
That's right.
And not having the Earth's atmosphere in the way.
Right.
I mean, Keck telescopes are bigger. They're 10 meters across, but they have Earth's atmosphere to get in their way, right?
That's right. And so then here's a comparison of the size of the mirror on Webb and the Hubble mirror, which is 2.5 meters across, and the previous infrared telescope in space, which was called Spitzer. It was launched more than 20 years ago. And again, the thing to take away from this is that the Webb has a much larger mirror than the previous infrared space telescope Spitzer. And a large mirror is important for 2 reasons. Number one, it allows the collection of more light and therefore the detection of fainter objects in the sky. And number two, a larger mirror produces sharper images. And so both of those features are illustrated here in this comparison of an image of a tiny little area of sky viewed with Spitzer 20 years ago, and then Webb just a few years ago after it was launched. And you can see how Webb, its image, is much crisper and sharper, and it detects much fainter objects. And again, that's because of its larger mirror.
Right. And I mean, the mirror is, let's see, so Webb is like 8 times the size of Spitzer's mirror, right?
Right.
Roughly that. So that, since the resolution is proportional to the mirror diameter, there you get 8 times the resolution. So every pixel in Spitzer becomes 64 pixels in Webb, right?
Right.
That's always kind of cool to recognize.
Right. And a key issue in terms of taking advantage of that resolution is having Spitzer in space, because the atmosphere makes stars appear blurry. And so it's really key to have that mirror out in space where we can take full advantage of its resolution. And so here's an image from 20 years ago from Spitzer of a cluster of young newborn stars called IC348. And this is one of the clusters that I've studied with Webb. And this cluster is located about 1,000 light years away. And so for perspective, our galaxy, the Milky Way, in which we live, is 100,000 light years across. So 1,000 light years sounds like a very large distance, but that's still our relatively small neighborhood in our galaxy. And this is showing the center of the cluster that we imaged in 2022 with Webb. And this is comparing the Spitzer and Webb images for that center of the cluster. And once again, you can see how much sharper and crisper and more sensitive the Webb image is.
Yeah, I'm always amused by the comparison Spitzer to Webb because it's such an amazing jump, right?
I mean, one thing I should point out is that when we obtained the Spitzer images like this 20 years ago, that was a huge improvement over what we had before. I mean, like for instance, Spitzer in this cluster, it's able to detect brown dwarfs down to about 10 times the mass of Jupiter, and so that was very impressive at that time. So Spitzer was very powerful for its time.
Absolutely. I mean, it sort of lasted for what, 20, 30 years, Spitzer, before it was retired?
A bit over a decade.
Okay.
It was launched in 2003.
2003, and then it was shut down just a few years ago. So that's like almost 20 years.
Right.
Yeah. Yes, each successive generation of telescope always gives this big quantum jump leap in availability.
That's
now,
right.
What about the wavelengths of Webb versus Spitzer? Do they cover basically the same wavelength region?
They do. So Spitzer spanned from 3 microns to more than 100 microns, although most of the work with Spitzer was done between 3 and 24 microns. And that is very similar to the wavelength range of Webb.
Because we've done a bunch of comparisons of, say, Hubble to Webb, where they have the inner overlap in the near infrared, right? Mm-hmm. And here you're able to give a really good comparison to Spitzer in the same wavelengths.
Right. So again, that was the area of this cluster that we observed in 2022. And based on the success of that work, which I'll show in a moment, we were able to obtain more images for a larger area of the cluster. And now the exposure times were actually quite a bit longer than what we obtained in 2022, which allowed us to search for objects at even smaller masses. And this is showing the color image from Webb for that larger field.
Why did it change colors? Is it just that you chose different colors for the same wavelengths, or are you observing in different wavelengths?
Yeah, so there's a lot of discretion that goes into choosing the colorization for images like this.
Right. I mean, we can't see infrared, so we have to give it some color. Right. So what is the choice here with that came up with the green? Is there some chromatic ordering to the filters?
So normally the convention is that the shortest wavelength is assigned blue, and the longest wavelength is assigned red, and then intermediate colors are at intermediate wavelengths, and that was what was done here. But it just turned out that given the wavelengths that we were looking at, the color image ended up appearing green.
Okay, because I mean, the previous image was so very red, and now this image is so very green. It feels like they're totally different objects.
Right. But again, I mean, if you asked another astronomer to create a color image from the same data, you might see significantly different color choices. Okay. So a lot of the colorization is sort of subjective.
All right. And so the other question that comes up is you're talking about this being a star cluster, but yet we're also seeing a lot of gas and dust here. What's the significance of having all that gas and dust around it?
Right. Well, so I mentioned earlier how stars are born from the collapse of clouds of gas and dust. And so what we're seeing here is the remains of the original cloud that formed these stars. And so in this cluster, we have about 500 stars and brown dwarfs that all individually collapsed from pockets in that original large cloud of gas and dust. And there's still some of that remaining gas and dust sticking around. But if we came back in another 5 million years, most of that gas and dust we're seeing here, it would have been blown away by the winds from the newborn stars.
Okay, great. Let's continue.
And now this is showing another comparison between Spitzer and Webb. But now this is just for a tiny little section of this new set of images. And so once again, you see how the Webb image is much sharper and detects much fainter objects.
Great.
So Webb is great for detecting very, very faint objects in a cluster like this. But now the question is, among the thousands of faint little things we see in these images, how do we know which of them are brown dwarfs versus distant background stars and galaxies?
Yeah, that's so true with so many things in the universe. It's like,
right,
you can't tell how far away it is unless you know exactly how bright it is, or vice versa.
Yeah, you're always trying to find the needle in the haystack, trying to determine how to distinguish what you're searching for from all the other objects in the universe. And so this is showing what are called filters. So a filter is a device in a camera that allows only certain wavelengths of light to be collected by the camera. And so this is the complement of filters available on the camera that we used in the Webb. And so what we did was we selected filters for our images of IC48 that would produce distinctive colors for brown dwarfs versus other stars and galaxies. And so that's how we identified possible brown dwarfs, is by obtaining images in filters that will produce very distinctive colors for brown dwarfs.
Okay, and of course, Webb only takes one filter at a time, right?
So it actually obtains images simultaneously for the same area in the left, with the filter on the left between 0.5 and 2.5 microns, and with the filter on the right between 2.5 and 5 microns. So you can choose one on the left, one on the right, and you take images simultaneously for the same area of sky.
Cool.
And so that's very nice. It's very efficient.
Right, and it improves your throughput. So if you've got a certain amount of time on Webb, right, your job as the scientist is to choose which filters, one from column A and one from column B, which filters are going to get you the science that you want out of it.
Yep. So like, for instance, in the case of our 2024 imaging, we selected 2 filters from the left and 2 filters from the right. And so using those 4 filters, that was enough to give us very distinctive colors for brown dwarfs and be able to separate them from all the other background stars and galaxies.
Okay, great.
And so by doing that, we're able to identify 43 brown dwarf candidates out of like 10,000 sources that were detected in total in those images. And so the next step to confirm those candidates as actual brown dwarfs is to perform spectroscopy on them, which we can use to measure their temperatures and confirm that they're actually cold, like we expect for brown dwarfs.
Okay, are you going to explain? There we go. I knew you'd have to explain spectroscopy. Great, go for it.
Yeah, so spectroscopy refers to taking light and spreading it into its different wavelengths, so that different wavelengths appear at different positions. And that's done, for instance, by a prism. And so the different colors in a rainbow correspond to different wavelengths, and we're seeing those different wavelengths, those different colors at different physical positions. And that rainbow that we see is called a spectrum. And there are instruments in the Webb that perform this function. They take light from distant objects in the universe, spread it out into its wavelengths. And it turns out that's very important, because when you do that, you can measure temperatures from that spectrum. And so, for instance, this is showing wavelength on the horizontal axis and the intensity of light on the vertical axis. And so when the curve is higher, that means brighter. When the curve is lower, that means fainter. And this is showing an example of a spectrum of a typical brown dwarf. And it turns out that brown dwarfs, because they're very cool, molecules are able to survive and form in their atmospheres. And those molecules, they like to absorb light at certain wavelengths. And so because of that, the spectrum will be fainter at the wavelengths where the molecules are absorbing light. And so that's why these troughs in the spectrum, they're labeled with different molecules that are responsible for those troughs.
Okay, it's probably going to, confuse some of our viewers that, here you've got 600-degree brown dwarf, but it still has water in its molecules in its atmosphere, right?
Right. So in this case, it's not liquid water, it's water vapor, it's steam. Because as you said, it's still hundreds of Kelvin, or even 1,000 Kelvin. So it's quite hot, so any water would be evaporated. And so what we want to do then is obtain spectra like this for our brown dwarf candidates and see if their spectra show these absorption bands due to molecules. And if they do, that'll confirm they're actually cold and therefore brown dwarfs.
At different temperatures, will the molecules that are present in these absorption bands change?
Right. So that's something I'll touch on later.
Okay.
Now, as you go to lower and lower temperatures, you see different molecules start to appear. So for instance, this brown dwarf right here is just cold enough that methane is starting to form. So we see a little feature from methane. But if we went to colder and colder temperatures, the methane absorption would become much more stronger because the methane would be much more abundant at those colder temperatures. And then if you go to even lower temperatures, you can actually see ammonia start to appear.
Cool.
And so this is showing then a dozen of the 19 brown dwarf candidates that we observed with Webb and obtained spectra with Webb. And so we found that 12 of the 19 were confirmed to be brown dwarfs that are newborn in the cluster. And so all of these brown dwarfs show these troughs in their spectra that indicate the presence of water vapor. And so this shows that these objects are cool.
Okay.
Now, as I mentioned a moment ago, brown dwarfs, if you go to low enough temperatures, they can also show methane potentially. And so we were wondering whether we would see methane absorption in any new brown dwarfs that we found. And so the blue line here is showing where methane should appear. So it's the same feature that's indicated here. But we didn't see methane in any of these spectra. Instead, we see a different absorption feature at a slightly longer wavelength. And this is labeled in red. And this feature is coming from a hydrocarbon that's not methane. It's some hydrocarbon that's more complex and larger than methane. But we don't know which one it is.
Okay.
So this is showing the structure.
Organic chemistry was really complex.
That's right. So this is showing examples of hydrocarbons that are in the same family of hydrocarbons as methane. So here's methane, and then here are larger and larger hydrocarbon molecules. And so we know that the feature we're seeing here is not methane, and instead it must come from some larger, more complex hydrocarbon that's in the same family as methane.
Okay.
And that was really neat because the only atmospheres in which these complex hydrocarbons had been seen before were those of Titan and Saturn in our solar system. So nobody had seen these hydrocarbons in atmospheres outside the solar system before these observations. And so this was totally unexpected.
So you're saying that Titan and Saturn, okay, but not Jupiter. Okay.
Jupiter probably very likely has the hydrocarbon, but Jupiter has not been observed with a certain kind of observation that you need to detect it. So in the case of Titan and Saturn, the reason the hydrocarbon was detected was because Cassini, it observed their atmospheres with the sun behind Saturn and Titan.
Right.
And by observing their atmospheres and observing sunlight passing through their atmospheres from that unique vantage point, they were able to detect this hydrocarbon in a layer of the atmosphere that's normally not easy to probe.
Okay.
And so in the case of Jupiter, Cassini doesn't orbit Jupiter, so because Jupiter has not been observed in the same way. But if it was, it probably would show this hydrocarbon.
Right. Yeah, because I mean, Jupiter's closer to a brown dwarf than Saturn is. So, okay, continue.
And so this is the same diagram I showed earlier, luminosity and temperature. But now I've color-coded the wavelength ranges that correspond to different speckle classes. So for many years, for a century, astronomers have assigned letters to different temperature ranges of stars and more recently brown dwarfs. And so, for instance, the coolest stars and brown dwarfs have been assigned classes of M, L, T, and Y.
Okay, so M dwarfs, L dwarfs, T dwarfs. Not terribly familiar with Y dwarfs.
Right. So Y dwarfs are defined by the presence of ammonia. T dwarfs are defined by the appearance of methane. And then the M dwarfs are defined by having what's called titanium oxide and vanadium oxide. So these different molecules define these different classes.
All right. And so basically, if you take a spectra of one of these objects and you see what absorption features it has, then you can have a good idea of its temperature and give it a spectral class letter.
Right. So for instance, if you see methane but not ammonia in a brown dwarf, you would assign that a class of T. But if you see ammonia as well, you would assign that a class of Y. And the reason that's important is that in this context is that we've now detected a new molecule that has not been seen in brown dwarfs previously. And so because of that, we proposed a new class of brown dwarfs. And we proposed the letter of H, which stands for hydrocarbon. And so this class of brown dwarfs will be defined by the presence of this hydrocarbon that's larger and more complex than methane.
Well, cool. I mean, that's like, why should it be? If it's the same temperature as a T dwarf, why should it have all this more complex hydrocarbon?
Yeah, that's a great question. That's a big mystery. I mean, nobody expected this. Everyone assumed that newborn brown dwarfs would show methane just like their older counterparts. But now we're seeing that instead of methane, they have a more complex hydrocarbon. But it's a mystery as far as why that's the case. We don't know why these newborn brown dwarfs are forming a hydrocarbon that's not methane. That's a big mystery.
That's the progress of science.
Right. Finding the unexpected. And so, as I mentioned, the whole point of this work was to try to find new record holders for the least massive brown dwarfs, try to better determine the smallest masses of which they exist. And in this case, 4 of the new brown dwarfs we found, we estimate they have masses about 2 times the mass of Jupiter. So that makes them the least massive known brown dwarfs.
Okay, so are you gonna tell us how you estimated those masses?
So what we did was we used the images to estimate the luminosities for these brown dwarfs.
Okay.
So remember, luminosity is on this diagram here.
Right.
And so once we estimated the luminosities, we could use models of brown dwarfs and the predictions for luminosities from those models to estimate what the masses should be. So given the age of this cluster and the luminosities, it's possible to infer where the masses should be.
Okay. Because unless you got something orbiting around it, it's hard to tell the mass of anything, right?
That's right.
Yeah. Cool.
So we don't know whether brown dwarfs exist at even smaller masses. To answer that question, what we need new images with longer exposure times that can detect even fainter brown dwarfs. And so potentially Webb could detect brown dwarfs approaching the mass of Saturn if they exist at those small masses.
Okay, now if they have the mass of Jupiter or Saturn, how come they're not a planet?
Well, so that's a great question. So that's because of how they form. So
it goes back to that formation thing we discussed earlier.
right. And so in the case of these objects, these two Jupiter-mass brown dwarfs, it's very likely they formed like stars, and therefore we would call them planets. But one complication is that we think that sometimes planets can be ejected from their star systems,
right,
and go wandering through space by themselves. So we think that the galaxy is full of free-floating planets. And so then the question is, well, how do you distinguish between a free-floating planet that was thrown out of its star system and a brown dwarf that formed like a star? And that's sort of TBD. We don't really know for sure how to distinguish between those two possibilities.
Yeah. They will look very similar to all observations.
But I mean, so one question you might ask is, well, how do we know that these objects we found here are not ejected planets? And the reason is that this cluster, it's only a few million years old. So there hasn't been very much time for planets to be born around stars and get thrown out of their star systems. So because of that, it seems more likely that these are brown dwarfs rather than ejected planets, just because there's been so little time for ejection to occur.
Right. Okay.
Now, this is showing the spectra for two of the brown dwarfs that we found. And you'll notice that one of them is brighter at longer wavelengths. And that is probably evidence of emission from cool dust surrounding that brown dwarf. So we think that the brown dwarf, whose spectrum is shown in black, it likely has a disk of gas and dust around it. And as I mentioned earlier, that those disks are important because those are the birth sites for planets. So planets are born in disks of gas and dust around newborn stars. And so here we found evidence for a disk of gas and dust around one of the two Jupiter-mass brown dwarfs. And so that then raises the possibility that tiny little planets might be in the process of forming around some of these brown dwarfs. And so there might be miniature solar systems out there in the universe where the central sun is only 2 times the mass of Jupiter, and it's surrounded by its own tiny little planetary system.
All right, and that leads us to one of these little questions. Could a brown dwarf solar system be habitable?
That's a great question. It's hard to rule anything out, but it seems less likely that planets would be habitable around brown dwarfs. And one reason is that because a brown dwarf cools and fades indefinitely forever, the distance at which the distance from the brown dwarf where the temperature will be right for water to be liquid on a planet,
right,
that distance would slowly move towards the brown dwarfs over time.
Right.
So that means that for any planet orbiting a brown dwarf, it's going to get colder and colder over time because the brown dwarf is getting colder as well.
Right.
And so what that means is that you wouldn't have stable conditions for billions of years.
Right. And it took billions of years for life to fully develop here on Earth. So we assume it takes that time scale elsewhere in the universe.
Right. But the thing is that the radiation from a star or a brown dwarf is probably not the only thing that affects whether water can be liquid on a planet. There are like tidal forces, for instance, like the moon Europa around Jupiter, we think has a liquid ocean under its icy crust. And that's not because of radiation from the sun, it's because of stretching and squeezing by the gravity of Jupiter. So it still may be possible that planets around brown dwarfs could have life. It just seems probably less likely than planets around stars having life.
Okay. One of our viewers knows that planets around red dwarfs are not thought to be habitable because the red dwarfs have lots of solar flares and ejections. Do brown dwarfs have similar flares and ejections?
So they do to some extent, especially when they're young, that they're very active, magnetically active when they're young. But as they cool and fade, we think that activity dies down a lot. So,
Yeah, I mean, there's less energy, so yeah, you'd expect the activity would go away. Yeah,
that's right.
Cool.
And so a few of the brown dwarfs we discovered in this cluster are not isolated. Instead, they're in binary systems. And this is showing two of the binary systems that we found. For both of these binary systems, the separation between their two brown dwarfs is roughly 80 AU, where 1 AU is an astronomical unit. That's the distance between the Earth and Sun. And so each of these pairs, the separation is roughly double the orbit of Pluto around the Sun.
Okay.
And what's neat about these two binary systems is that their masses are quite low. As indicated here, one pair has masses about 6 and 12 times the mass of Jupiter. The other one is about 8 and 18 Jupiter masses. And so that makes these two pairs among the smallest known binary systems.
Cool. I mean, we've got binary stars, and now we've got binary brown dwarfs.
That's right.
And those are going. So, I mean, so many O stars, really massive stars, are in binary systems. So even your most massive stars, all the way through your regular stars, all the way down to your failed stars, come in binary systems. Gravity is doing it the same thing on many different mass scales.
So it turns out that how often you find binary systems, it's related to the masses of the objects. So it turns out that binary systems are less common as you go to lower and lower mass objects. So for instance, in the case of brown dwarfs, only maybe 10 or 15% of them are in binary systems. Whereas for stars like the Sun, roughly half of them are in binary systems. So the binaries are less common around brown dwarfs than around stars. That's something that's been known for many years.
Oh, that's cool. All right, great.
So this is just showing the Webb image for the center of IC38 once again. And so one neat aspect of this work is that image was submitted to the US Postal Service as a suggestion for inclusion on a new stamp, and it was selected for a stamp last year. In this case, it was published on a Priority Mail Express stamp. That's the largest denomination of stamps issued by the Postal Service. And so that was a kind of an unexpected bonus from this work.
Well, the Postal Service seems to really value these small brown dwarfs.
Right. And so it turns out at that same time, there was another Webb image of a galaxy, of a nearby galaxy that was also selected for a stamp, and it's shown here.
In fact, I think that's pretty much the image I have in back of me, but with a different color scheme.
Right. It's kind of, I think it's rotated around maybe.
Yeah.
And so on this subject, one thing I thought I would mention is the following. So in the case of Hubble images or Webb images of galaxies, the high resolution of those images allows one to measure very detailed structure in galaxies. And that's scientifically important, as you can imagine, but it's also very aesthetically appealing. So my point is that, like in the case of galaxies, there's usually a direct connection between the visual appeal and the scientific value. But in the case of our cluster that we observe with Webb, the aspect of the image that makes it visually appealing is this extended diffuse light from the gas and dust in the cluster. So that makes it visually appealing, but it turns out that ironically, that diffuse light is actually an obstacle to my work. For instance, I mean, that extended light makes it more difficult for me to see the tiny, faint little brown dwarfs in the cluster.
You're trying to get a firefly, and you get all this background light to be able to find that firefly.
Right. But this is a sort of thing it's hard for me to avoid because, as I mentioned earlier, I need to search for brown dwarfs when they're newborn, which means searching for them in these nebula. And these nebula typically have this diffuse light. So it's just something we have to live with, given the hunting grounds that we've selected for these brown dwarfs.
I mean, you got to look in places where newborn stars are.
That's right.
There's going to be a lot of gas and dust there.
Yeah, so it's hard to avoid.
Cool.
Okay, so that's all I have for my talk. I'm happy
That's
to
all
take
your slides.
questions.
Okay, great, fantastic. We got some more questions for you. You've already sort of answered this. The question reads, how small does a brown dwarf's mass have to be before it might possibly be classed or mistaken for a gas giant? And you've talked about you can get them down to 2. We might be able to get them below that. So it sounds like there's a class of objects that if you just know its mass, you don't know whether it's a planet or a brown dwarf.
Right. So one thing I didn't mention is that what is the mass range of planets? So gas giant planets around stars, they extend up to about 15 times the mass of Jupiter.
Okay.
Right. Yeah. So planets go from 15 Jupiter masses down to the mass of Mercury or smaller. And as we've seen, brown dwarfs extend all the way to 2 Jupiter masses. So that means that brown dwarfs and planets, they overlap for a pretty large range of masses, between 2 and 15 times the mass of Jupiter.
Okay.
And like you said, what that means is that in many circumstances, it can be difficult to distinguish between whether you found a planet or a gas giant planet or a brown dwarf.
Right, because you can't look at something and say, oh, that was obviously formed at the center of a disk, or it was formed out in a disk, unless it's surrounding a star.
Yeah, I mean, sometimes there's circumstantial evidence. So for instance, I showed earlier that one of those brown dwarfs we found, it has this disk of its own. And so that tends to suggest that it probably formed like a star since it has its own big disk.
Cool. So when we think of stars, the most massive stars are the rarest stars. And as you go down in mass, you get lots more. Does that continue to brown dwarfs? Are brown dwarfs much more common than red dwarfs, which are much more common than yellow dwarfs, etc.?
It's a great question. So it turns out that the most common stars are those between about 0.1 and 0.2 solar masses, between 10 and 20% the mass of the sun.
Okay.
Now, once you go to lower masses into the brown dwarfs start to become more and more rare. And so the peak of that distribution of stars and brown dwarfs, it's around 0.1 to 0.2 solar masses. So among the least massive stars.
So the most in the universe, if we were to count all the stars in the universe, the most stars that we would find would be between 10 and 20% the mass of the sun.
Right. And another number I can give you is that it turns out that stars outnumber brown dwarfs by about a factor of 5. But there are 200 billion stars in our Milky Way, so that still means tens of billions of brown dwarfs.
Okay.
There's still plenty of them around.
But in terms of the mass budget of the Milky Way, brown dwarfs aren't going to, be the new missing dark mass or whatever.
That's
right?
correct. That's correct.
Okay. All right. Let's see. Okay, so would a system that could only form a brown dwarf, okay, so you're collapsing a brown dwarf in the center, have enough stellar mass to form rocky planets? So you talk about a disk around a brown dwarf. Mm-hmm. Would there be enough mass in that disk to form rocky planets?
That's a great question. We don't know for sure. So for more massive, the most massive brown dwarfs that are like between maybe 60 and 80 Jupiter masses, for those, we have some measurements of the masses of the disks around them when they're newborn. And so we have some sense for how much material is available. But when you go to lower and lower masses, it becomes more and more difficult to measure the masses of their disks. But basically, the rule of thumb is that for stars and brown dwarfs, the mass of its disk when it's newborn is about 1% the mass of the central object. So if we have a 2 Jupiter mass brown dwarf, the disk around it probably has a mass of 2% the mass of Jupiter. And so then the question is, what sort of planets can you make out of that? So maybe you can make a Mars-sized planet, but it's probably going to be difficult to make it anything bigger than that.
Okay. So, I mean, the planetesimals would be the that are created would be limited by the amount of mass available for that.
Right, but again, that's uncharted territory. We don't really know very well the kinds of planets that might form in these situations.
Right. I mean, we can barely see the brown dwarfs. It's going to be a long time before we can actually see the material in the disks around that.
Right.
Okay. So Mark Lowitz, could two brown dwarfs in a binary brown dwarf system, each with a mass just under the upper mass limit, merge to form an M dwarf star? Could we get blue stragglers, but with brown dwarfs, basically?
Yeah, certainly. I mean, in theory, that could happen. The question is, what would lead to that merger? And so what could happen is if you have a triple system, so three bodies,
yeah,
where one gets ejected, that ejection might lead to the other two objects merging together. So in theory, that could happen. It probably would be very rare, as you might expect. And I don't think that anybody's actually seen evidence of that happening yet, but it could happen.
Fantastic. All right. Those are all the questions that I think. Ralph, did you have any questions that you thought would be cool to ask in here?
Yeah, actually, I had a question about a previous question about stars, planets, rocky planets potentially forming around these brown dwarfs. I know, like, when a star ignites, it sends out this outward pressure, blowing dust and gas away from it at that point. Does a brown dwarf also have that that pressure on the surrounding disk? And if it does, is it as strong, or will that affect planet formation around the brown dwarf if it doesn't have that stellar pressure that you expect from a star?
Yeah, and that's a great question. I mean, that's what you're describing is a whole field of work where, I mean, even for stars like the sun, there's a lot of uncertainty and debate about, like, after a star is born, what is it that clears away the disk and leaves behind the planets? And that's a whole field of study just for stars, let alone brown dwarfs. So for brown dwarfs, it's likely the radiation probably helps to sweep away some of the gas and dust in the disk, but as you can imagine, that radiation is weaker, and so it might be less efficient. And so, I mean, you might expect that the disks around brown dwarfs might survive longer because there's less radiation from the central object to blow that matter away. And we actually see some evidence for that. So we see that disks for low mass stars and brown dwarfs, they do seem to survive longer, for like tens of millions of years, whereas the disks around solar mass stars like the sun, they seem to disappear more quickly in only a few million years. But again, that's all a whole area of research that where there's still a lot of uncertainty.
Gotcha. That's interesting, because I'm almost picturing just an enormous asteroid field, disk around it, because the material can linger there longer.
That's right.
It doesn't have as much force on it. So I thought that would be kind of interesting. Yeah. Any questions? I personally, because I work as an illustrator, I'm always trying to picture what these things look like. And so
Ralph and I were just discussing T-Tauri winds the other day.
Yeah, it's very interesting. So with sorry, I am multitasking a little bit, so I'm sorry if I ask anything that you've already answered. But I was also curious, like brown dwarfs, so they are luminous. How would they look optically, to human eyes? If you could take a camera up to a brown dwarf, would it be really, really bright? Would it be kind of like a dull red, a burning stove or something? Or what
at visible wavelengths that our eyes can see, it would look dull red. Okay. Although, again, it would depend somewhat on the temperature and the age. So when they're very young, there's moderately warm, 3,000 Kelvin. And so they might look like a red dwarf star. But then if you're looking at a T dwarf or a Y dwarf that's billions of years old and in only a few hundred Kelvin, at visible wavelengths, they basically look black. They wouldn't be shining at visible wavelengths, only in the infrared. I mean, you can think of Jupiter. So if you looked at Jupiter without the sun around, Jupiter would look black because it doesn't produce any visible light of its own.
Right.
And we think about heating a bar of iron. Right, iron really glows at 2,000 degrees, but at hundreds of degrees, you don't really notice it. It's still
That's
just
right. Yep, exactly right.
a dark mass.
Very cool. So I guess it wouldn't be bright enough to read at night, or if you happen to be on one of those little rocky planets, you probably couldn't read very well.
Well, you would need infrared eyes. You'd like to be a predator.
Yeah.
I wish I had infrared eyes.
Well, if life developed around a brown dwarf, the eyes would be developed to see in that light, right?
That is true. I did also wanted to point out, like, I'm really glad that you brought up Spitzer in comparison with Webb. Something I've found oftentimes, talking with people in the public, most people generally know about like Hubble and Webb, and so when they hear, there's often comparisons between Hubble and Webb, and it's not always a fair comparison because they're completely different wavelengths of light. They see different things. Maybe not, I don't know if it's completely, maybe there's some overlap, but so it's nice to see that, like, the Spitzer being an infrared telescope, it's a more fair comparison to look at. So I really appreciate seeing Spitzer as this is what we could see with this, and this is what we can see now.
Yeah, I mean, that is one of the things that when people wanted to say, oh, Webb is the successor to Hubble, it's really the successor to Spitzer, but it has the same keen resolution that Hubble has. So it's like a combination of both of them, which that's the way I like to think about it.
Yeah. Let's see. There was one question here that I thought was kind of interesting. Was are brown dwarfs capable of producing higher energy emissions, such as gamma rays, X-rays, UVs, or anything like that? I imagine you have to get pretty hot to produce something like that.
So they can generate X-rays. So in general, young stars are X-ray active. They have huge corona, and that applies to brown dwarfs when they're young as well. So young brown dwarfs are X-ray active, and we've seen examples, even old cool brown dwarfs still show activity at X-ray wavelengths to a little bit, to some degree. Although, as you can imagine, it gets a lot weaker. But they don't produce gamma rays, as far as we know. And UV wavelengths, the only time you would see UV radiation is if you have a newborn brown dwarf that has one of these disks of gas and dust. As the matter is falling onto the brown dwarf surface, that can generate a shock that produces UV radiation, but that's only something that's happening for the very youngest brown dwarfs. Otherwise, they really shouldn't produce any UV radiation.
Okay.
Huh.
Well, go ahead, Ralph. You have more?
Oh yeah, sorry. I just have one more question. Sort of based on that was, when we're looking at things like this that are kind of like, on the boundary of one thing and another thing, right? It's like it's really hard to tell, when is something a rogue gas giant versus a brown dwarf versus a star or whatever. Are there any characteristics, physical characteristics of like a star that you might find on a brown dwarf? Things like flares or solar prominences or even like sunspots. Like I know some of that is going to be driven by magnetic fields and such.
Yeah. Do we know much about magnetic fields on brown dwarfs?
Yeah, there's some measurements.
Cool.
So one similarity that I already mentioned between brown dwarfs and stars would be those disks. So again, if you see a large disk, relatively large disk around a brown dwarf, that's reminiscent of a star. Whereas gas giants that are formed within disks around stars, we think they also have tiny little disks, but they're much, much smaller than what you would find around a brown dwarf. And so that's one common characteristic between stars and brown dwarfs that you wouldn't find for planets, are these relatively large disks that are like a few AU in size. And then also it's possible that the atmospheric compositions might be different between gas giant planets and brown dwarfs, but that's still very uncertain. It's not clear how much they might differ, but there might be different abundances of different molecules in a gas giant planet versus a brown dwarf. So there's been some hope that spectroscopy of those molecules might be able to provide clues about how one object formed versus another. But that's still an open area of research.
Well, I think I love about astronomy.
It's going to keep you busy for quite some time, I can tell. All right, Kevin, thank you so much, illuminating some of the smallest stars or the largest planets in the universe, one or the other or both. This has been fantastic. Folks, come join us for our next Deep Space Dialogues, March 18th, Klaus Pontoppidan, what Webb is showing us about planet formation. And now you see that my preview was right, because Klaus is going to talk about planet formation. Here you got the full gist on brown dwarfs, and then you'll be able to put them all together. That'll be cool. All right, so thank you very much, Kevin. Everyone, have a wonderful day.
Thanks.